Hi there, I'm Nick and this is Reinforced, a show where we're going to help you improve your design for 3D printing skills and have some fun along the way. Today we're going to be talking about strength. So specifically, how we can improve the Z-axis strength of our 3D printed parts. And if you stick with us for a couple minutes, I can guarantee you that I can help you make some of your parts instantly stronger with just a little bit of redesign. So let's dive in. If you've been around 3D printing at all, you've probably heard that the Z-axis is weaker than the XY plane or in each layer of a 3D printed part. This can be a problem because you may not expect that part to have those different properties in different directions. You may expect to have a uniformly strong part. So why should you care about the strength in the Z-axis? Well, you want it to avoid broken parts. Imagine you were using a part like this and didn't realize that it didn't have enough strength and you assumed it was going to work, and all of a sudden when you put it into practice, it splits down the middle, cracks, and ruins your day. No one wants that, and so that's why we need to think about how to reinforce those parts against those weaker axes. Having stronger parts will mean that you can use 3D printed parts in more applications, give you more capabilities in those parts, and just generally make 3D printing a more useful tool in your everyday work. So the first thing we need to talk about is this word, anisotropy, or the characteristic of having different material properties in different directions or axes. So a classic example of anisotropy is wood. Have you ever cut down a tree or split a log? So if you have, you probably noticed that it was easier to split that log along the grain than against it. And that's anisotropy at work. The wood is very much stronger in one direction than another. So wood's just one example of anisotropy in nature, but you've probably run into others around you. And guess what? 3D printing also is anisotropic. I should be a little bit more specific there because there are some 3D printing processes that are more or less anisotropic than others. So when we're talking about 3D printing today, we're going to be talking about filament extrusion 3D printing, like what you'll see with your Markforged machine, amongst others. And so if you're building a part layer by layer and extruding plastic or composite fiber into that part, you're going to see anisotropy between the layers. And this is where the classic example of 3D printed parts are weak in the Z-axis comes from. So let's talk about that. Let's talk about why 3D printed parts have different strengths in different directions. And it comes down to two things: material properties and sort of geometric or physical bulk properties of the part. On the material properties side of things, we're really looking at how polymers bond together. Let's look at an example. We're building a part, in this case, out of a chopped carbon fiber and nylon material. So nylon's a polymer, and without getting too much into the chemistry behind it, that means it's a material made out of a lot of repeating chains of different chemical units. And those chains, when you heat up that polymer and heat up that nylon and melt it, those chains can actually entangle, and when it cools down, they're trapped together and they form a really strong bond. And this is generally what's happening when you lay down a layer of plastic in your 3D printed part. Now the challenge is always that if you melt the layer below it fully, you're gonna turn your part into a puddle. Wah, wah. So we have to have a balance between the amount of melting that occurs between layers and still preserving the integrity of the 3D printed part that we've already done. That's the engineering trade-off we make in filament extrusion 3D printing. We're always going to have a somewhat weaker bond between layers than we will with the continuous extrusion path in the layer. Okay, so that's the first driver of anisotropy in your 3D printed parts. But there's also a component that's due to the physical structure of the part. So a couple areas here. One, we're building a part layer by layer. So you've probably seen a 3D printed part and seen the layer lines or the sort of scalloping effect, even if it's a very microscopic effect. So if we apply a load to that part, those ridges and those layer lines are really concentrating the forces kind of between those layers, which is the worst possible place for that force to be. And because of that, that can act as a crack initiator, and it's the start of a part failing under loads or oftentimes impact. So the other thing we have to deal with is infill. For purposes of speed and using less material, most 3D printed parts are printed with a sparse honeycomb or triangular infill, but the downside there is you now have less material in that part. So when we think about material properties of something like, maybe machined aluminum is often just a solid, homogeneous metal. With a 3D printed part though, because it's not solid, we also have to think about the strength properties that results from that infill. We have less material, so it's gonna have less strength in that area. And the combination of all of these things leads to anisotropy in our 3D printed parts. So if we wanna make our 3D printed parts stronger in the Z-axis, we need to counteract the effects of this anisotropy. So that's what we're gonna do today. We're gonna talk about some strategies to reinforce your parts against these weaknesses that you see oftentimes in the Z-axis. And that brings us to my favorite thing to talk about. So if you've been through our Markforged University course, you've probably heard me talk about functional requirements, but I'm gonna talk about them again. Y'all know I love functional requirements, and we're gonna do that right now. So functional requirements are thinking about what it is that your part actually needs to do. What are the loads it needs to resist? What are the environmental conditions that it has to deal with? How does it interact with other parts? So as an example, I want to use this CNC bending die. CNC tube bending is a process where you use a CNC machine that can bend all kinds of different complex geometries into tubes and pipes. And a lot of times you'll need custom dies to get you the bend geometry you want. These dies can be expensive to machine and have long lead times. So it does make sense to try to 3D print them if we can make the capabilities match the functional requirements of this part. So let's talk about what some of those functional requirements could be. So a CNC tube bender will take a straight tube and will bend that tube around this die. So those tubes could be steel, they could be copper, they could be aluminum, all kinds of different materials that can get formed by a machine like this. And depending on the material of the tube being formed or the wall thickness and a bunch of other factors, there can be quite a lot of force on a part like this. So as the CNC tube bender forms this tube, it's gonna bring a tube in and then push it in against the die. And that's going to cause this die to want to separate or split in this direction. So the first thing we want to figure out is where's my Z-axis? Because we can't know where the Z-axis or interlayer weakness is without knowing how this part was printed. So we want to know what's the print orientation. Well, in this part, we printed it like this on the build plate. So the Z-axis is going up this way, and our layers are stacked up and down like this. So that'll let us know where the layers in this part are and where that Z-axis weakness starts. That means that our first functional requirement for a 3D printed CNC bending die is to make sure that this expansion force produced by that tube coming in doesn't split the part between layers. So that leads us to our first strategy. So if there's a force trying to separate the layers in the Z direction, and really it's producing a expansion force, the first thing we need to do is counteract that force. So we can do that with bolts. Let's take a closer look at this bend die over here and see what that looks like. So you'll notice the first thing I've done is that I've put captive nuts in pockets along the bottom of the part. And on the other side, you can see that I've driven bolts all the way through the part that thread into those nuts. These are really simple changes that I've made to the design of this part, and I've done them in CAD. And all I did was just add some holes and the pockets for those nuts and bolts. So the result of this is that I've added the tensile strength of those bolts to the overall Z strength of the part. And because those bolts are sandwiching this part together, they're actually helping also stop crack initiation at the bottom of this bend region. So that's our first strategy to reinforcing parts in the Z-axis, which is simply to add bolts and nuts that compress the whole part together and add some compressive strength in the Z-axis to resist any forces that are going to try to separate those layers. So our next functional requirement in this bend die is to think about how the machine is going to transfer torque to the die and what the forces are going to be on the part with that. So let's take another look there. So the way that the tube bender applies torque and rotation to this die is through two machine keys that lay in this channel right here. And as the machine applies torque and rotation to the die, those transfer that force and help rotate the die itself. Now, the problem with that is that the die was designed for a material like steel, which is going to have relatively uniform strength all throughout the part. But we're using a 3D printed die, which has that anisotropy that we've been talking about. So we need to figure out how to resist against the forces that this die is going to see. Now, when those machine keys exert a force on the die, they're really only exerting it on a small region of layers near the top of the part. And the problem with that is, as soon as the machine key stops, it's basically causing a massive shear force at that bottom layer. So as you might expect, if we didn't reinforce this die any further, that area right here would probably just shear off as that machine key just pushed all that material over. Because it's really only focusing that force on this upper section of the die. And while it wouldn't split like this part did, because the force in this example was top to bottom, it would still kind of just slide off that layer or try to push off that section of layers. So we need to find a way to take this local force that's all in shear and distribute it out through as many layers as we can in the z-axis so that it doesn't cause the part to fail. And that's my next strategy for reinforcing parts between layers. You'll notice that I designed in machine keys of my own that run all the way through the part. And so these metal machine keys are the contact surface for the larger machine keys that are attached to the tube bender. So machine keys like this are a really cheap, easy off-the-shelf solution to adding flat surfaces which have metal properties, so wear resistance and strength. And it's something that I use pretty often when I'm designing parts that need capabilities beyond what a 3D printed part can offer. So with these machine keys running all the way through the part, we now take that force, that shear force, that the key from the tube bender would apply to the part, and it's distributing out over the entirety of the z-axis of this part, and that means that we're no longer seeing any sort of failure due to that torque. So between those two solutions, bolts in the z-axis and then machine keys to act as that wear surface and that flat that also distributes out that shear force, we now have an effective solution that resists all of the forces and meets all of the functional requirements of the CNC tube bending die. So we can generalize these types of solutions to other off-the-shelf components as well, all in the name of reinforcing your parts against their weaker axes. An easy way to think about how to address the functional requirements of your part is to really think about the loads and forces and the things that it really needs to do. And then from there, kind of take it a step further. What if this force caused this part to fail? If it did, how would it fail? And how would it deform or deflect or things like that? So it's a good thought exercise to go through that. And that's a good way to start thinking about how you're going to solve that problem. You'll walk through all those different functional requirements, think about how each one would impact the part, and then produce design decisions that can adjust or remedy those functional requirements or address those functional requirements with a 3D printed part. So I hope you found these design techniques useful, and I want to hear from you. Let us know in the comments below if there's something you'd like us to cover or a challenge that you're working through. Or maybe it's just something that you printed and want to share with us. If you enjoyed this content, make sure to hit the like button below and subscribe to see more of Markforged Reinforced. Thanks for watching and happy printing.